Hakime. I am a PhD student in Boğaziçi University in Turkey. And thank you all for coming. I hope this doesn't feel boring after this exciting tutorial. So today I will talk about our study that introduces... Okay. I will talk about our study that introduces a representation for the proteins using their interacting ligands. So the definition of the proteins in the computational space has a major importance because many bioinformatics tasks such as protein function prediction, prediction of the interactions between proteins and ligands, and proteins or protein clustering or protein classification, all of these tasks depend on how we represent the proteins. So the most common way to represent proteins is using their sequences, but the sequence alone is not always enough to completely understand the whole protein mechanism. And even though we use sequence to determine protein structure, high sequence similarity is not always indicative of structural similarity or functional similarity. So in this study, our goal is to build a new representation for proteins. And we want this representation to integrate functional characterization of the protein. And our main motivation was this puzzle-like interaction between the protein and its interacting ligands, because the previous studies showed us that we can use a ligand to capture functional and mechanistic properties of proteins, such as the study that showed a strong correlation between the protein architecture and its bound ligand. And similarly, Kaiser et al. And Hart et al. Showed that we can actually use chemical similarity to detect protein similarity. So in the light of these studies, we built our proposal. It was to represent proteins using their interacting ligands. And this is a simple schema of our model. And you can imagine these two ellipses as the proteins, and the diamonds are their interacting ligands. And the first protein have 2 distinct ligands, and the second one have 4 distinct ligands. And in a nutshell, we can say that a protein is equal to the average of its interacting ligands. So in our system, for a pair of proteins, the more ligands they have in common, the more similar they will be. And in order to define the protein, we need to first define the ligand itself. So ligands can be described in 2D representation, which looks very similar to a graph. So many graph-based algorithms use this representation to compute similarity. And there are also fingerprint representations that is based on using this substructure information in the protein, mainly categorized under structural or hash-based fingerprints. There is also this representation called SMILES, and it is a text-based approach, and it uses specialized characters to represent the chemical information in the ligand itself, such as the atoms, bonds, or branches. So since SMILES is simple, so it is also text-based, so it can be, we can use many text similarity algorithms on it if we want to compute a similarity of 2 ligands using their SMILES string. And indeed, in a very recent study, we showed that using the SMILES-based representation, we obtained competitive scores with the method that uses graph-based representation in protein-ligand interaction prediction task. And the SMILES-based representation was exceptionally faster to compute ligand similarity when compared with the graph-based algorithm. So based on these information saying that SMILES is simple and text-based, we can apply as many as text-based algorithms on it. And one of the methods that we use is a form of distributed word representation. The term itself is old, but it's regained its popularity with Thomas Mikalov's recent study called Word2Vec. And what Word2Vec does is, it is a neural network-based learning, and it is trained on a very large text corpus. And in the end, it outputs a vector representation, a high-dimensional and real-valued vector representation for the words in this corpus. If we are working on English words, this corpus might be the whole Wikipedia articles. So representing words in these vector forms, we can simply compute this similarity, but how related these vectors are really and how related they will be in their real life meanings depend on the power of the algorithm that used to create these vectors. So the power of word2vec comes from that it considers the context of each word that it appears. So in the end, the vectors we have semantic meanings, saying that, for instance, the difference between the king and man vectors would be equal to the difference between queen and woman vectors. So if we go to the chemical space, we have our SMI string, and if we think this SMI as a Wikipedia article, we need to find words for our algorithm to train on. So the easiest way to create words from a series of characters is just using the sliding window approach. We move the pointer one letter at a time with a fixed character length. In this example, our character length is 4, but it can be any number. So if we go to the distributed word representation, we have our ligands to represent, and we said that we will use this SMI string, and we extracted words from this SMI string, and we need our algorithm to train on something. So for English words, if we want to learn a representation for the English words, our training corpus would be the Wikipedia articles. But right now we are dealing with SMI string, so our corpus should consist of SMI string and the words that we will extract from this SMI string. So we can use PubChem or Campbell databases to collect this information. And in the end, as we did with the word vectors, we have now representation for these words that I call chemical words. We have representation for them. But what we actually try to achieve is to create a representation for the whole chemical, which is equal to the whole SMIs. So the simple thing we can do is just taking the average of all of these chemical words that we initially extracted from SMIs. So taking the average would be equal to the representation of the whole SMIs, which now we will refer as SMIs-vec. Okay, let me remind you our initial goal. We actually tried to build a representation for the protein, and we said that we will use their interacting ligands. And so far, we decided that we will use SMI string, and on top of that SMI string, we trained a neural network-based algorithm and created a high-dimensional and real-valued vector representation for the SMIs that we call SMIs-vec. And now we will move on with the protein. And here is a sample protein, and it has 2 interacting ligands, which are types of methylboronic acids, tamam beta-lactamase protein. And using the pipeline we described before, we have representation vectors for these interacting SMIs that we use their SMIs. And again, the simple way to create the vector representation for the protein, we just simply take the average of the SMIs-vec of its interacting ligands. And now we have a representation for the protein that is purely based on SMI string. And we tried to assess the performance of how well this SMIs-vec-based representation actually describe the protein. So we adapted protein clustering task and clustered protein into families and superfamilies. We used 2 popular clustering algorithms, transitive clustering and microclustering algorithm. And as for data set, we also use the scope database, but it has some subsets called astral data sets. Here we specifically used a 50 data set. It means that the proteins in this data set have at most 50% sequence similarity. And initially in this data, in this subset, a 50 subset, there had 11,000 proteins, but since our approach requires protein to interact with ligands, we took the proteins that have at least an interacting ligand, so we filter out the ones with no non-ligand interaction. And our pipeline for the protein-ligand interaction collection, we took the scope ID of the protein and went to UniProt. And using that UniProt ID, we collected the interacting ligands from Campbell along with the SMI string of the ligands. So these clustering algorithms depend on the similarity between proteins in order to divide them into the small clusters. So we compared SMI-SIG-based protein representation with the protein similarity approaches in two categories. The first one is a sequence-based category, which has BLAST, which is a very popular way to compute protein similarity that uses local alignment. And PROTVEC is another approach. It also uses the same distributed word representation method word2vec, but it uses protein sequence. The second category, it is also a ligand-based approach to protein, but instead of SMI-SIG, we now use a fingerprint-based approach, extended fingerprint model. So here are the results. Actually, our results, we compared more than these, but they are detailedly explained in the paper. These are just simply for better illustration. So here for SMI-SIG, we selected actually our words to be the 8 character because we found out that 8 is the optimum best solution, and we trained these SMIs from the ones that we collected from Campbell. And for PROTVEC, we select the protein sequence to be 3 character words. So in the end, you can see that BLAST had the poorest F measure value when compared with the rest of the 3 algorithms. And among these 3 algorithms, you can see that the ligand-based approaches provide very competitive scores to PROTVEC that uses protein sequence. So as for the ligand-based approaches, you can see that SMI-SIG is also very competitive with the extended connectivity fingerprint model, even though this fingerprint model implicitly contains the chemical structure information, and SMI-SIG just depends on text-based model. And we can say that since both of these ligand-based approaches obtained very close scores, this ligand-based protein representation is actually a consistent model and independent on how we represent the ligands. So this is a simple case study that we choose from our results, and it's a clustering of a sample superfamily. We have 7 proteins from the same fibronectin type 3 superfamily, and as you can see that they are in SMI-SIG clustered together, but PROTVEC, which is based on sequence similarity, it clustered them into 4 different clusters, and it even clustered this protein on its own. So when we further investigate this protein, we saw that it had only 2 interacting ligands, and it shared this interacting ligand with another protein in the same superfamily. So we can say that SMI-SIG, using this ligand similarity and ligand sharing information that is encoded within its vector representation, it achieved to cluster these proteins from the same superfamily together. So in conclusion, we propose an approach to represent ligands using their SMI string that we called SMI-SIG, and it provided competitive scores with the fingerprint representations, and we also proposed an approach to represent proteins using their interacting ligands, and this approach also provided well even in the absence of any sequence or structure information of the protein. And we can especially suggest this information to identify new protein-ligand interactions or protein function annotations. We have, however, limitations of our study, and since it's dependent on protein-ligand interaction information, our model is available for the proteins that have known ligand interactions. We right now use Campbell to collect these interactions, but we aim to enrich our data to include metabolites from other databases as well. I gratefully acknowledge my advisors and our kind sponsors, which helped me to be here today. And thank you so much for your patience and listening.
So thanks for that talk. It's really interesting. So something I noticed is that the way you're computing sort of your vector describing a protein is just simply a average in some space of the vectors of describing the individual ligands. If you're doing that in some sort of Euclidean space, then presumably you have some sort of metric for distance between vectors. And then if you have that, could you compute, for example, given your set of ligand vectors, a standard deviation or some measure of error in what you are calling your vector describing the protein? And then from that, would you be able to make some estimate as to how many interacting ligands you need in order to confidently say this is a good way of representing the protein?
Okay, that's a nice question. We right now only used what we have in Campbell, so for some proteins it is limited because not all proteins have interactions in Campbell, but some of them has more interactions, so we didn't do any that kind of assessment, but it would be good. Thank you.
Do you think your method could work with peptides instead of ligands? Peptides bound in protein that you represent as smiles?
Peptides as the I'm not very familiar with these peptides, but I think they are a little more bigger than the ligands, right?
Usually, yeah.
Yeah,
But will that be the limitation?
I don't think so. But okay, does these peptides also have these spatial interactions just as the proteins and ligands have too?
Yeah.
Yeah, then that would be something to that can be used to characterize the protein, since that if that peptides especially connects that specific protein.
Thanks.
Thank you.
Yeah, just a quick question. How many dimensions do your vectors have?
We used 100 dimension, but tried up to 300, but 100 worked well. Thank you.